Understanding inputs, wheels or tires. The dowel optimizer was purpose-built for concrete slabs that support vehicular traffic, from carts with steel casters to forklifts to large over-the-road trucks and even straddle carriers at ports. We'll start by entering a single wheel load of 4,850 pounds. Next, select the wheel or tire type. This choice affects the allowable differential joint deflection and the optimization. For small hard wheels, the limit is 0.01 inches, about the thickness of 2 stacked dollar bills. For solid rubber or cushion tires, the limit is 0.02 inches. And for pneumatic tires, like those on standard trucks and cars, it's 0.035 inches. These values are based on ACI guidance except for pneumatic tires, where no clear industry standards exist. Let's choose solid rubber for this example. Now enter the wheel or tire spacing, typically the distance between 2 tires on either side of an axle. In this case, we'll input 36 inches on center. This spacing relates to how loads interact in the slab. If the spacing is large, specifically if it approaches or exceeds twice the value of the radius of relative stiffness, then the loads act independently, and their effects are not additive. If the loads are closer than this, then it's possible that we must consider both loads when determining the critical dowel load. The example so far reflects a 4,000-pound capacity lift truck based on input assumptions from Walker and Holland's performance-based dowel design. Now, let's add the last 2 inputs, wheel or tire width and length. These 2 inputs are often missing in older designs, and they can be taken or calculated from the data sheet for a specific vehicle. Let's say we're using a 6-inch wide rubber tire. If the tire length is unknown, you can estimate it based on the contact pressure. For example, with the load of 4,850 pounds, a contact pressure of 400 psi, and a 6-inch wide tire, the estimated tire length is 2.02 inches. It's fine to enter 2.02 inches, but since this input is relatively insensitive, you can safely round down to the nearest whole number. That completes the example for a 4,000-pound capacity traditional lift truck. Let's try another, a 4,000-pound pallet lift truck with wheel load and spacing again from Walker and Holland. Here we have a 2,000-pound single wheel load with small hard wheels spaced 18 inches on center. These wheels are often 3 inches wide, but again, the best source is the vehicle's cut sheet. For tire length, the contact area is often so small it's nearly invisible. To be conservative, let's assume the contact pressure is close to the concrete compressive strength, say 4,000 psi. This gives us a contact length of just 0.17 inches. You can input this value, but to simplify, the dowel optimizer allows 0 inches as an input for tire length. With the tire length set to 0 inches, we have effectively made a concentrated line load. If you're looking to design for a concentrated load, just input 0 for both the length and the width. Now let's look at a larger vehicle, like an 18-wheeler. If you have a 20,000-pound steer axle, then each tire supports 10,000 pounds. With a contact pressure of 130 psi and a width of 11 inches, our contact length is 7 inches. So your inputs for this 20,000-pound steer axle are 10,000 pounds, pneumatic tire, 80-inch spacing, 11 inches wide, and 7 inches long. If an axle has 4 tires, you can model half of it. For example, a 17,000-pound axle with 4 tires means 4,250 pounds per tire. At 11 inches wide and 130 psi, the length is roughly 3 inches. These dual tires might be spaced 12 inches apart, leaving a 1-inch gap between them. Whether your design involves small pallet jacks or large industrial trucks, the dowel optimizer gives you the flexibility to model a wide range of realistic loading conditions. Once you've entered the values for the design vehicle, click Continue to move on to the structure inputs.